Good morning to all of you. I am Tamojit Pal and you all are welcome to my channel. In the previous video, we have learned that a current carrying conductor will produce a magnetic field. We know that Hans Wester, he started this experiment and he accidentally discovered this property, that magnetic effect of current. That is, if there is a flow of current, then it will obviously produce a magnetic field. So we all know that. Now in today's lecture, I will discuss on some topic. Let us note down the topic. First topic I will discuss magnetic field. Second topic I will discuss trajectory of charged particle. In magnetic field. Third, Biot-Savart law. Fourth, application of Biot-Savart law. So this fourth topic I will discuss today, and in the next video I will discuss the remaining part of the chapter. So not for wasting more time, so today I will discuss on this fourth topic. So the first topic is magnetic field. What is magnetic field? Now we have already learned about electric field. That is, if an electric charge is there, then it will produce an electric field around its boundary. Okay. Now in the same way, we will discuss or we will define magnetic field. First we have to bring a magnet here. This magnet will exert an influence around it. Now we all know that electric field, it extends towards infinity. Okay, it extends towards infinity. So we cannot take the infinite limit. So we have to limit ourselves within a boundary, and we have to define that boundary, and within that boundary we will experience the electric field or electric force. In the same way, we will define magnetic field. First of all, we have to define a boundary here. Beyond this boundary, the magnetic force will be negligible, so we can consider it as 0. So within that boundary, it will have some effect, and within this boundary, if we bring a isolated north pole. Now one thing I have to mention here, the important thing is that magnetic monopole does not exist. Magnetic monopole does not exist. We cannot separate North Pole and South Pole. But there is a difference with electric field. In electric field, we have electric charge, we have monopole of electric field, or we have monopole of electric charge. That is, we can take single positive charge or we can take single negative charge. But in magnetic field, we cannot take single North Pole or single South Pole. So this cannot be possible. But theoretically, we can define an isolated North Pole or South Pole. It is an imaginary thing, a theoretical thing. It cannot be in practical. So we can theoretically assume a magnetic North Pole here. So this magnetic North Pole will experience an attraction towards this North Pole or North Pole of this magnet. And extremely sorry, this North Pole will feel an attraction towards the South Pole, and it will feel repulsion from the magnetic North Pole. Okay. So this North Pole will this North Pole will experience a force, due to this magnet. So what is magnetic field? Magnetic field is nothing but a space or a boundary around a magnet, within that boundary. If we bring a magnetic North Pole, or if we bring an isolated North Pole, then it will experience a force due to this magnet. So we have defined magnetic field. So this is the definition. Actually, magnetic field, it is a region within which the magnet will experience a force on this isolated North Pole. Okay, and we denote magnetic field by the symbol B, and it is a vector quantity. Just like electric field, it is a magnetic field, and it is also a vector quantity, and we denote this magnetic field as B. Okay. So I have defined the magnetic field. What is magnetic field? Magnetic field is nothing but just a region around the magnet. Now the second point is the trajectory. Trajectory of electron. How will be the trajectory of electron if we bring it within a magnetic field? Suppose the magnetic field is in this direction. And we bring a charge particle, and the charge particle will have velocity in this direction. Okay. We will bring a charge particle, and the charge particle will have velocity in this direction. Then what will happen? It will experience a force. Now, before this, I want to tell about the magnetic force. What is magnetic force? What is magnetic force? Before discussing the trajectory of the electron, we have to define what is magnetic force. Okay. So see, magnetic force, it is denoted by Fb. One important thing we have to notice. See, a current carrying conductor, it will produce a magnetic field around it. Now we bring a charge particle here. Suppose the charge particle is Q. Now there is two things. First case is the charge is in stationary, and second case is the charge is in motion, that is, it has a velocity. So see, a current carrying conductor, it has both magnetic field as well as electric field. It has electric field because the charge particle is in motion. So there is a charge particle, so it will produce a electric field. Along with it will produce a magnetic field because the charge is in motion. So moving charge will always produce a magnetic field. We all know that. So this current carrying conductor will produce electric field as well as magnetic field. Okay. So here we have both electric field as well as magnetic field. Now, if we bring a charge particle here, okay, the charge particle has two cases. One is in stationary case, and second one is in motion case. One is in stationary, the second one is in motion. Now, if the charge particle is static or stationary, then only and only electric field, electric force will experience over it. If the charge particle is in stationary, then only electric field will exert a force on this charge, and it will produce an electric force. Only and only electric force will be exerted on the stationary charge. Now, if the charge is in motion, suppose it has velocity v, then this moving charge will experience both electric force as well as magnetic force. So, interesting thing is, this is very interesting. A current carrying conductor, it has a moving charge, and due to the presence of this charge, it will produce electric field, and as the charge is in motion, it will produce a magnetic field. So here we have both electric field as well as magnetic field. Now we will bring a charge here. The charge will have two conditions. It may be in stationary state or it may be in motion. The two states, either stationary or in motion. Now if the charge is in stationary state, then it will experience only electric force. If the charge is in motion, then it will experience both electric force and magnetic force. So, if the charge is in motion, then it will experience both electric force as well as magnetic force. The main funda is it. So, I think it will be clear. Now, we know that electric force, its value is Q into E. E is the electric field and F is the electric force and Q is the charge. We all know this. Now, if we have to calculate this magnetic force, then its value will be the charge, the amount of charge into V cross B. This will be the formula of magnetic force, that is, if B is equals to Q into V cross B. This will be the formula of magnetic force. Now see, F equal to Q into V cross B. Now V is the velocity. Suppose this will be the velocity. Okay. And the magnetic field. What will be the direction of the magnetic field? We all know the formula of Eastern experiment. Okay. Now we will place a thumb. We will place the palm over this electric current in such a way that this fourth finger will show the direction of the current, and this thumb will give the direction of the magnetic field. So the magnetic field will be in this direction. Magnetic field will be in this direction. Then what will be the direction of the force? What will be the direction of the force? As it is in cross product. So the direction will be V cross B. So V cross B. So the direction of the force is outward of the plane of the board. Okay. So what will be the direction of the magnetic force? That is V cross B. So the direction of the force will be outward of the magnetic plane. Okay. So see, the magnetic force is perpendicular to V. The magnetic force is perpendicular to B. Okay. This magnetic force is perpendicular to V and B. Now see, as the magnetic force is perpendicular to V, then we can say that the force is also perpendicular to displacement. Magnetic force is also perpendicular to the displacement. Since the magnetic force is perpendicular to V, that is the velocity of the particle, then we can say that this force will be perpendicular to the displacement also, because the V is displacement by time. So the magnetic force will be perpendicular to the displacement. Now since force is perpendicular to the displacement, we can say that the magnetic force, it is a no work force. No work force. Since the magnetic force is perpendicular to the displacement, we can say this is a no work force. That is, what does it mean? It is meaning that, its meaning is that this magnetic force will do not perform any work. Okay, this magnetic force will do not perform any work. So we have get an example of no work force, that is a magnetic force is a no work force. Okay, so we have get the formula of magnetic force. Now we get the trajectory of the electron, or we will get the trajectory of the electron or any charged particle. Any charged particle. So suppose V is in this direction and B is in this direction. V and B, that is V is the velocity of the electron and B is the velocity of the electron, and B is the magnetic field. And suppose, first of all we will take a condition, a special condition, that V and B is perpendicular. That is F equal to Q V cross B. So Q V B sine 90 degree, and this will be Q V and B. So V is in this direction and B is the perpendicular to the V. Now we all know that force, that is F, that is magnetic force, will always perpendicular to V and B. So what will be the direction of the force? Now say V is in this direction and B is in this direction. So V cross B. V cross B. So outward. The force, the direction of the force will be the outward of the plane of the board. So the force is in outward direction. Okay? The force is in outward direction. Okay? Now, what will be the trajectory of the electron? Now think in 3D format. Think in 3D format. The electron or the charged particle move in this direction. When the charged particle come at this point, the force is direction. The direction of the force will be outward to the plane. So this charged particle will be forced to move outward of this plane. Till now, the electron or the charged particle is just moving along the plane. As it moves, it will experience a force outward to the plane. As the force is direction to the outward of the plane, the electron or the charged particle will experience a force outward to the plane, so it will move outward. The charged particle will come outward. At the same way, at every point, it will be direction to the outward of the plane. Now think in 3D format, it come outward. Think in 3D format, it come outward. At this point, again it will experience a force outward of the plane. It will move again outward. At this point, again the force will be in outward of the plane, so it will move outward. In this way, it will experience a circular motion. Let us take another example. Suppose B is in this direction and V is in this direction. Fine. You see, the direction of the magnetic force will be V cross B, V cross B. Again, the force will be in outward direction, outward to the plane of the board. Now, as the charged particle move from origin to towards the V, it will experience outward force, so it will come outward. Again, at this point, the direction of the velocity is in this direction, V, and B is perpendicular. So see, the direction of the force will be V cross B, V cross B. The direction will be in this direction. The force, the direction of the force will get changed. So in this direction, the charged particle will move. Again, at this point, the velocity is in this direction, and magnetic field is in this direction. So V cross B, the force will be in this direction. So it will move in this direction. Okay. Here also the velocity is in this direction. V cross B, V cross B, the force in this direction, so the charge particle will move in this direction. So ultimately it will it will form a complete circle. Okay. So we can say if the angle between magnetic field and velocity is perpendicular, that is they are perpendicular, that is it will if the two vectors will form an angle 90 degree, then the charge particle, the moving charge particle will form a circle. So the trajectory will be circle. I think you have understand. Okay. You can try it on yourself. You will get understand. Or you can rewind the video and can understand. Now the second thing is that suppose the velocity is, suppose the direction of the magnetic field in this direction and velocity is in this direction, and it will have a angle theta. These two vectors will form an angle theta. Then what will happen? We all know that the direction of the force will be V cross B, V cross B. Think 3D. Suppose velocity, magnetic field is in this direction and velocity is just in the z plane, xz plane. This is x and V is in xz plane. It is outward xz plane. V is out xz plane. So V cross B, V cross B. See, B is in xz plane and B is in x axis. B is in x axis. B is in x axis and V is in xz plane. This is z outward to the normal of the plane of the board, and this is V is in xz plane. It is in xz plane. I think you have understand. So the direction of the force will be V cross B, V cross B, V cross B. So the force will be upward. Now see, as the particle move, it will experience a force in upward direction, so it will move upward. At the same point, the V is in this direction and B is in this direction. So V cross B, V, see, this is the plane, and the charge particle, it move upward. Since it will experience a force in the upward direction. So V is in this direction, so V cross B, V cross B, V cross B, V cross B. So it will experience a force in this direction, so it will turn around. In this direction, the V is in upward direction and B is in this direction. V is in upward direction and B is in this direction. So V cross B, V cross B, this direction. It will again move upward and curve, slightly curved. Now see, it will experience a spiral motion, and its axis will be the B axis. Its axis will be the axis of the magnetic field. Okay, it will form a helical path. If the direction of the magnetic field and the direction of the V will form an angle, will extend an angle theta, then it will form a helical path. If the angle between B and V is perpendicular, that is 90 degree, then it will form a circle. Okay, so this is the trajectory of the electron in the magnetic field. Okay, so this will form a helical path. Now the next thing, the most important thing of this chapter is the Biot-Savart law. Biot-Savart law. What is it? Through this law, we can derive the magnetic field of any geometrical figure. Through this formula or through this law, we can derive the magnetic field of any particle, of any conductor, okay, of any conductor, or any shape of the conductor. The shape may be different. We can derive the magnetic field. So through this law, there are four things. There are four statements. The first statement is dP. That is, now see, this Biot-Savart law is very important. The Biot-Savart law, this is actually valid for only elementary magnetic field. dP is the elementary magnetic field. Elementary magnetic field. What is it? See, this is the conductor. Now it is carrying the current I. Now suppose we have to find the velocity at this point P. So we have to find the magnetic field at this point P. What we will do? We just cut an elementary length of this conductor. Say that elementary length is dl, and due to this elementary length, it will form a magnetic field over this point, and this magnetic field will be elementary magnetic field, that is dB. Okay? Due to this elementary length, this portion also it will have a current, and this elementary field, this elementary length, due to this elementary length, it will produce a magnetic field on the point P, and this magnetic field will be this elementary magnetic field. So the Biot-Savart law is valid for elementary magnetic field. Now after deriving this elementary magnetic field, we have to integrate for whole conductor, and we will get the magnetic field for the whole conductor. Okay. So this, according to Biot-Savart law, this elementary magnetic field is proportional to number 1, the current I. If the magnitude of the current increases, then the elementary magnetic field will also increase. Number 2 is directly proportional to dl, the elementary length of the elementary length of the conductor. dB is inversely proportional to r square, radius square, distance square. Suppose from this elementary length at the point P, it has the distance r. As the distance increases, the elementary magnetic field will decrease, and it will decrease at the square rate. Okay, so this is inverse square law. Okay. The fourth thing is that, see, the direction of the elementary length is in this direction, that is the direction of the current, and the direction of the distance is in this direction. This is the direction of the this is the direction of the distance, and this is the direction of the elementary length. So these two vectors will extend an angle theta. These two vectors will extend an angle theta, and this elementary magnetic field will be directly proportional to sine theta. Okay, sine theta. So this is the four laws stated in the Biot-Savart law. Elementary magnetic field is directly proportional to the current carrying the conductor, directly proportional to the elementary length that we have extended, inversely proportional to 1 by inversely proportional to distance square, and directly proportional to sin theta. That is, theta is the angle between dl and, okay. So we can combine these four laws. dp is proportional to I dl sin theta by r square. Now, to omit this proportional sign, we have to bring a constant here. This constant is mu0 by 4 pi I dl sin theta by r square. Okay, this mu0, it is the permeability of the free space. This is the permeability of the free space. What does permeability means? I will discuss this permeability in the next video. Actually, it is a property of the medium. It is a property of the medium. If the if the medium has greater permeability, then the magnetic field line will pass through that medium very easily. Okay. So this is the permeability. I will discuss this permeability in details in the next video. Okay. So this is the thing. This is a Biot-Savart law. Okay. This is the magnitude of elementary magnetic field. And as we calculate the elementary magnetic field, to find the magnetic field for the whole conductor, we have to integrate. We have to just integrate this. Okay. Now, this is the magnitude form. If we want to derive the vector form of this magnetic field, then dB is equals to mu0 by 4 pi I dl elementary length cross b I dl cross r by r cube. This is the vector form. This is the vector form of elementary magnetic field. Okay, just copy it out. Here is it. Now comes the fourth topic, that is application of this Biot-Savart law. Okay. First, I will derive the magnetic field for a long current carrying conductor. It is a straight long current carrying conductor. Carrying current I. Straight, long current conductor. Straight long current carrying conductor. Okay. Now, suppose I have to find the magnetic field at the point P. The perpendicular distance from the conductor to the point P, let's say A. Okay. This is the two end point A and B, and this is the O. This is the O. So from point A, from point A and from point P, you have to draw a line here. This is the distance of two extreme points from O. Okay. Let's say this makes an angle theta 1 and this makes an angle minus theta 2. This point makes an angle minus theta 1, it is going in minus direction, minus theta 1, and this will be in plus theta 1. Okay, plus theta 1, minus theta 2. Okay. Now, how we find the how we apply the Biot-Savart law? So let's first cut out a elementary length dl, and from this dl, let's say, let me change the color. Suppose this is dl, and from this dl, the point P, let's say the distance is r. Okay. Now from point O, the length is, the distance will be L. Okay. And let's say naming this dl point, let's say it is C. Okay. So it's make a triangle OCP. Okay. What we have done? First of all, we have cut an elementary length dl, and from this dl, the distance from P to the dl is r, and this elementary length is situated at a distance L from the point O. Okay. You have to describe all the things you have done in the exam. Okay. Now see, according to Biot-Savart law, we can say dB, that is magnetic field due to this elementary length, that is elementary magnetic field, will be mu0 by 4 pi I dl sine theta. Now see, this theta is the angle between dl and r. Now see, dl is, and this direction is in this direction, that is according to the actually towards the direction of the flow of the current, and r is, its direction is in this direction. Okay. So the angle, let's say this angle is phi. Let's say this angle is phi. So sine phi. Okay. And this angle, let's say this angle is theta. Okay. Ideal sine theta by r square. Okay. So taking the magnitude of dV. Now see, in triangle POC, that is this triangle. Okay. This is theta, this is phi, this is L, this is R, this is A. Or all is known, but everything is given here. This is P, this is C, this is B. Okay. Now see, dl. To find dl, we have to first calculate the value of L. Now see, tan theta is perpendicular by base. Perpendicular is this L, and base is A. So L is equals to A tan theta. Now differentiating in both sides, dl is equals to A sec square theta d theta. We can derive it. Same way, let us take cos theta. Now cos theta base by hypotenuse, cos theta base by hypotenuse, base is A and hypotenuse will be R. Okay. Therefore, R equal to A cos theta, that means A sec theta. Therefore, we can say R is equals to A sec theta. This is number 1 and this is number 2. Now, putting the value of dl in here and putting the value of R in this equation. Let's say this equation is A. Okay. Now putting equation 1 and putting equation 2 in the equation A. If we put this value in this equation, we will get mu 0 by 4 pi I. Now sine phi, sine phi, sine phi we can write it as perpendicular by hypotenuse. Sine phi is perpendicular by hypotenuse. Now perpendicular will be A and hypotenuse will be R, and this is again A pi R, that is R is equals to R is equals to A by A sec theta. There will be cos theta. Fine, cos theta. So sine phi will be replaced by cos theta, and dl, if we put the value of dl, then it will be A sec square theta d theta, and R will be A square sec square theta. Okay, now this sec square and this sec square is cancel out, and is A and A will cancel out. What we will get, let us erase this part, just copy it out, pause the video and copy it out. Erase it. This will be mu 0 by 4 pi I cos theta d theta by A square. Now see, to find the magnetic field for this whole conductor, we have to integrate for the whole length of the conductor. So dv integration mu 0 by 4 pi I and A is constant, and this will be integrated with respect to theta, cos theta d theta. Now the direction of the theta will be from minus theta 2 to theta 1. From minus theta 2 to theta 1, the limit of the theta. So P is equals to mu 0 by 4 pi I by A cos theta. If we integrate cos theta, then we will get sin theta plus sin theta. Sin theta from minus theta 2 to theta 1. Therefore, we will get B is equals to mu 0 by 4 pi I by A sin theta 1 minus of sin minus theta 2. So B will be mu 0 by 4 pi I by A sin theta 1 plus sin theta 2. This is the derivation. This is the magnetic field at the point P due to the whole conductor. Okay. So this is the thing. Now see, we have taken the conductor of finite length. If we extend its length to the infinite in both sides, it is let's say it is an infinite long current carrying conductor. Infinite, that is, the both end of the conductor will limit to the infinite, that is, it is extending. So in that case, this P point will be very much close to length of the conductor. So let's say A, it is A. Now see, if we draw Actually, it is the point, the end point. It is at infinite. So from infinite, if we draw the r vector, and in this, if we draw the r vector, then it will extend an angle almost 90 degree. In the same way, in this direction also it will be extend almost 90 degree angle. Okay, it will extend almost 90 degree angle in the both side. So we can say theta 1 is 90 degree, theta 2 is also 90 degree. Then B is equals to mu 0 by 4 pi I by A sine theta 1 plus the sine 90 plus sine 90. It will become mu 0 by 4 pi 2I by A. This is B. So this is the magnetic field for a infinite current carrying conductor. Okay. Copy it out. Now, we have to derive the magnetic field for a circular loop. Circular loop. For a circular loop. Okay. This is a circle here. Okay. This is a radius. This is the center, and the radius of the circle is R. Radius is R. Now we have to find the magnetic field at any point on its axis. Now the axis of this of the ring. This is a ring here. It is actually, this is a circular ring, and it is carrying a current of I. Now this is the axis. This is the axis. So P is the point on the axis. Suppose this is a ring. This is a ring, and we have to find the magnetic field at this point. We have to find the magnetic field at this point. Okay. This is the axis. This is the axis. This is the axis, and we have to find the magnetic field at this point. Okay. Now let us extend an elementary length of dl here. Now this dl, from this dl we have to draw a line. It is distance. Sorry. This distance, let's say it is r, and this from point O, that is, let's say from the center, it is point O to P, the distance will be x. Okay. Now we have to find the magnetic field at the point P, and the elementary length, that is dl, to the point P is r. Now see, the direction of the dl is in this direction, and r is in this direction. Now if you think in 3D format, suppose this is the ring and D is in this direction. D is in this direction. Actually D is in this direction. Okay, D is in this direction, and we have to find the point at this point along the axis. Okay, this is the point P. Now see, this is actually the case. Now we have to find the magnetic field at this point P. Okay. Now the distance from this dl to P is just like this. Just like this. Just like this. It is just like this. Just like this. D is in this direction and R is in this direction. Now see, this DL and R, this DL and R is in right angle triangle, right angle. This DL and this R is in right angle. So DL is perpendicular to R. So sin theta is sin 90 degree, that is 1. Okay. So dB is equals to I dl by R. Sin theta is 0. Okay. Now let's say this angle is theta. Now again, we have to say this is a thing, this is the actual thing, this is the actual thing here. Now see, the direction of the magnetic field will be dl cross r. I have told that the vector form of dB is equals to mu 0, that is something k, to I dl cross r by r cube. So dl cross r. Now see, at this point, dl is in this direction, dl is in this direction, dl is in this direction, and r is in this direction. So r is in this direction and dl is in this direction. So the direction of the magnetic field at this point P will be dl cross r. dl cross r. So magnetic field will be in this direction. dl cross r, that is magnetic field will be in this direction. In this direction. dl cross r, this direction. So magnetic field will be in this direction. Okay. dB is in this direction. Okay. This angle will be on theta. Now see, this angle is in 90 degree. 90 degree. This angle is in 90 degree. Okay. Just naming this point as A, B, and this point is P. AB and this point is P. This angle